This video is about a little 5-inch diameter 3-phase axial flux alternator I built. It's mostly 3D printed. It's got 5-inch diameter steel discs. These are 1/8 of an inch thick. The bearings are in between the rotors in a little hub, and they're pressed into the hub, and the whole thing rides on this shoulder bolt that goes right through the middle. So this whole alternator could bolt onto whatever assembly I want, ideally a small wind turbine. The 3 bolts that go through the middle, idea here being if they're long enough, I could bolt a 3 to 5 foot diameter rotor on there, depending on how I wind the coils. If I furl early enough, I think we could run a 5-foot rotor on here. This one has 8 magnets per rotor. The magnets, I'll show you these parts over here. The magnets are 1-inch diameter, 1/4 inch thick discs, neodymium, N42 grade, and they fit into these holes on these discs. The back disc on the alternator is drilled out bigger in the back. It needs to be to accommodate hardware back there. Anyhow, that's a pretty simple setup. This just kind of holds the magnets in, and then around that whole assembly I printed another piece to fit over the front to sort of contain it and center everything, a bit like this here. This is a little 4-inch machine that I've got. I show parts of that in a different video. It's similar to this. I started this one, but I abandoned it because it's only got 3/8 inch bearings in it. I wanted something a little more robust should I actually run it as a real wind turbine. The coils fit in here, and I wound them on this form. This form is exactly the diameter of these holes, and the coils, once I take them out of here, I keep the center in, which is also 3D printed, and I can press them right into here. Once they are pressed in there, I could get this all loaded up with 8 coils, and then I put it on wax paper, and I put super glue in all the coils and put it down on the wax paper and fold the wax paper over the top, and then I pressed it down pretty hard so that the whole stator comes out to be 3.2 inches thick. And that's given me quite a bit of, a fairly safe clearance between the coils and the magnets. This is one of the coils I wound. I scrapped this one because it didn't come out real clean. But I only scrapped 1 coil in the process. I mean, you can see how they... No, that's not actually one. I'm sorry, let me get the right one. This one. This coil is a pretty good fit there. It expanded a little bit when I took it out, so like I said, I scrapped it, but you can see how it does fit in there pretty good. This coil is a little hard to build because it's really tight with the 5-inch rotors and the hub to accommodate the 3 bolts. I could have wired things up on the outside here, and that would have been all right. Maybe if I'd have made a little trough or something, or made this a little bigger. I only left this much room in the middle to make connections, which is feasible, but it's tight, and it's a little bit tricky. But it works. Each coil, I've got loads of 20 gauge wire kicking around, so I wound these out of 20 gauge wire just to get some data. Each coil is 120 turns, which fills this up perfectly. 120 turns. of 20 gauge wire. Each coil weighs right at 2.2 ounces, and that gets me a total stator resistance. If I wire in star, 2 coils per phase wired in star, so the resistance of 4 coils there comes in at about 1.7 ohm. So with that information, if we have volts per RPM, we can pretty much calculate a power curve. And I'll do that in the next video. I'll shortly put it on this hub, which fits on there, and put it in the milling machine here. Actually, I'll just run it in this video. Hold on a moment. Okay, I've got the hub on there now. Doesn't wobble too bad. So now I can put this in the mill, put it in the vise, and get it squared up with the chuck as best I can. Something like that. See what happens here. Actually, I'm going to loosen this a lot. I'm going to have to slow the mill down. I don't want to start up too fast. Looks a little crooked there, doesn't it? Okay, let's start the 3-phase converter here. I'm going to slow the mill down and start this up at about 150 RPM. This reads a little bit fast. It gets more accurate as I come up in the numbers, but I know that when it says about 285, that's actually exactly 300. I've checked that with frequency. So I've got the chuck loose. That way I can slow the machine down. Okay, now I've got a meter on one phase of the AC, and I think it's chucked pretty good in the mill here. So we'll start out at about 150 RPM. And it's at right about 4.5 volts AC, RMS AC, which is pretty good. This alternator too, when you short it out, you can feel pretty dramatic drag on it. So it's pretty efficient for a little tiny alternator. I'll bring it up to 300. It should be about double. Well, it'd be exactly double if my RPM is right. So yeah, 9 volts AC, 300 RPM. I'm going to see if I can scare up a 3-phase rectifier and put a load on it. But really, for now, that's kind of all the testing we need. We know stator resistance. We know volts per RPM. If we rectify this, we would multiply that AC number times the square root of 2. So really we've got a little, we're at right about, if we rectify, we'll be right at about 12 volts DC at 300 RPM with this little alternator, with the stator resistance of about 1.7 ohm. So That'd make a cool little 12-volt charger, wound just the way I have it. 300 RPM is actually a pretty reasonable speed to hit battery voltage for a 4-foot diameter wind turbine. And that just kind of worked out by luck, because I just wound it with the wire I had on the forms I made. But as I've mentioned in other videos, voltage is directly related to the number of loops in the coil. So if I wanted to wind this with, say, 23 gauge wire, I could have 12 volts DC at about 150 RPM. If you did 26 gauge wire, I know some people are playing with 26 gauge wire and small alternators, you would be hitting 12 volts DC at about 75 RPM, and you would be in for about 480 turns of wire in this particular platform. Fun stuff anyhow. Actually, I found a 3-phase rectifier kicking around, so I'll rectify this real quick and we'll play a little bit more. Okay, now I have all 3 phases hooked up to this 3-phase rectifier, which I assume is good. I don't think I ever used this one. And now I'm looking at DC volts. Assuming all these jumpers are good, I think they are. We had 9 volts here before, a little over 9 volts at 300 RPM. We can multiply that times the square root of 2 to look at the top of that sine wave, which is what we're rectifying, and that's what we'll see. So I would expect about 12 volts minus the square root of 2, because, or minus about 1.4 volts, sorry. We multiply 9 times the square root of 2, which is about 1.4, but then we have to subtract about 1.4 for the diode losses. So that will get us up to maybe 10.5 volts. We'll see. DC. Looks like the chuck came loose. I'm wrong, it's higher than I thought. 11.5 volts. I guess that makes sense. That's direct current now. So we can do some other experiments with direct current. So I got it all hooked up here and put a load on it. But because things aren't quite running square, and I put a load on it so there was torque, my little hub broke here. So I might fix that and get back to this. But at any rate, it doesn't matter a lot. We can make predictions based on stator resistance and open voltage. Pretty fun little alternator. Okay, I fixed the hub, sort of. I expect it'll probably break again because I just put some super glue on it. But there's our 11.5 volts DC at 300 RPM. I've got a 9 ohm load on here right now. If I hook this up, you can hear the load, you can see the spark. Listen and watch. So that'd be a little over an amp. That's 11, well, it was 11 volts into 9 ohm. Voltage dropped to